Hello everyone, I am Swarna Latha, working as an assistant professor in the Department of Electronics and Communication Engineering. Today's lecture, we are going to discuss about the problems on the power spectral density of an LTA system. In the previous lecture, already we have finished the power spectral density of an LTA system. So what is an LTA system? If for the LTA system is nothing but the system has to satisfy both linearity and time invariant property, then the system is called as LTA system. So if the input to the LTA system is x of t and its impulse response is h of t, then what is output y of t is equals to x of t convolution h of t. Now instead of giving this known input, we can give the random input x of t. Then what is output of that LTA system is also a random output, which is given by what? X of t convolution h of t. And then we have seen the power spectral density of the input and the power spectral density of the output. So these topics already we have discussed in the previous lecture. So on this, today we are going to discuss the problems. The first problem is a random process x of t is applied to a linear system whose impulse response is h of t equals to e power minus 2t for t greater than or equals 0. If the autocorrelation function of the process is Rxs of tau is equals to e power minus mod tau, find the power spectral density of the output process y of t. So it means what they have given here. So they have given x of t is a random process. So this random process they have applied to a linear time invariant system. So the input is what? X of t. And what is response is nothing but y of t. And what is impulse response of the system is h of t. Then what is y of t equals to x of t convolution h of t. So they have applied a random process x of t and a system whose impulse response is h of t is equals to e power minus 2t for t greater than or equals to 0. And it is 0 otherwise. So this is the impulse response they have given. After that, they have given the autocorrelation function of the random process x of t. The input random process x of t is given by e power minus of mod tau. So what they have given? E power minus of mod tau. And they have given the impulse response is h of t equals to e power minus 2t. So e power minus 2t for t greater than or equals to 0. Now, so they have given the autocorrelation function of the random process and they have given the impulse response of the LTA system. We have to calculate the power spectral density of the output random process y of t. So what is the power spectral density of the output random process which is interval what? S y of omega. So this is nothing but what? The power spectral density of the output random process y of t. Nothing but sy of omega. Now, if you know the power spectral density of the input, then how do you calculate the power spectral density of the output sy of omega equals to what? Mod of h of omega square into sxs of omega. Here, what is h of omega is nothing but what? The transfer function of the LTA system. The transfer function of the LTA system, that is nothing but h of omega equals to Fourier transform of h of t itself. Actually, this is nothing but what? Y of omega by x of omega, that is nothing but Fourier transform of the impulse response gives the transfer function of the particular system. And here, sxs of omega is nothing but the power spectral density of, if it is y is nothing but the output random process y of t. In place of y here, we have x, nothing but is a power spectral density of the input random process x of t. So, in order to calculate the power spectral density of output, first you have to find out the Fourier transform of the given impulse response and then you have to calculate the power spectral density of the input. So, if you know the autocorrelation function, then how do you calculate the power spectral density? You know the relation between autocorrelation and power spectral density, which is called as Wernicke generation. What is that relation states that the autocorrelation function and the power spectral density both form a Fourier transform pair. That is nothing but the Fourier transform of the autocorrelation function of the random process. The input random process x of t is nothing but what? The power spectral density of that input x of t. Now, calculate Sx of omega, nothing but the power spectral density of the input random process x of t, that equals to what? Fourier transform of what is Rx of tau they are given is nothing but e power minus of mod tau. So, what is the Fourier transform of the autocorrelation function? Fourier transform formula. So, if x of t is a function, a signal, then what is Fourier transform? Is equals to integration minus root infinity x of t into e power minus j omega t dt. But in place of t, I have the variable tau. Therefore, to write down the Fourier transform of Rx of tau as what? Integration minus infinity Rx of tau into e power minus j omega tau d tau. Thus, in place of t variable, I have the variable here tau. Therefore, replace it by tau now. Now, what they are given? The autocorrelation function they are given as what? E power minus of mod tau into e power minus j omega tau d tau. So that equals to, how can you write down the mod tau value? So what is mod tau equals to? Minus tau for negative values and plus tau for positive values. Therefore, how can I write down here? For negative values, nothing but from where to where? From minus into 0, nothing but these are the negative values of tau. So, for negative values of tau, what is mod tau value? Minus tau. So, minus tau into minus nothing but plus tau. Therefore, e power tau into e power minus j omega tau d tau plus positive values. So, from where to where the positive values? From 0 to infinity. So, 0 to infinity, nothing but these are the positive values of tau. So, for positive values of tau, what is mod tau value? Tau. Therefore, you will get e power minus tau into e power minus j omega tau d tau. So that equals to integration minus infinity 0 e power, if you take common, then if you take e power tau common, you will get 1 minus j omega. So 1 minus j omega into d tau plus integration 0 to infinity. If you take e power minus tau common in both the cases, then you will get e power minus tau into 1 plus j omega into d tau. So that equals to, what is the integration of e power tau into 1 minus j omega with respect to tau? Nothing but what? So e power tau into 1 minus j omega by 1 minus j omega. And what are the limits of tau here? Minus infinity to 0 plus, and the integration of e power minus tau into 1 plus j omega is nothing but e power minus tau into 1 plus j omega by, so minus of 1 plus j omega, and what are the limits of tau here? From 0 to infinity. Now substitute the upper and lower limits, then what can happen here? E power 0. So 0 into 1 minus j omega nothing but 0. So e power 0 value nothing but 1. So e power 0 minus e power minus infinity by 1 minus j omega, because tau value is minus infinity. Minus infinity 1 minus j omega nothing but minus infinity here. So plus, similarly here, substitute the upper limit, then what can happen here? In place of tau you have to substitute. So e power minus infinity into 1 plus j omega. So infinity is something you are going to get infinity only. Therefore here e power minus infinity minus, what is the lower limit here? 0. So the 0 into 1 plus j omega is 0. So here 0 by minus of 1 plus j omega. So that implies, so what is e power 0 value? 1. So 1 by 1 minus j omega. So here minus of minus are going to get plus. So plus 1 by 1 plus j omega. So that equals to, what can happen here? If you take LCM, we are going to get here 1 plus omega square. And here 1 plus j omega plus 1 minus j omega. We are going to get 2. So 2 by 1 plus j omega square. Therefore, what is the Fourier transform of e power minus mod tau? Nothing but 2 by 1 plus omega square. Now, the Fourier transform of nothing but Sx of omega is equals to what we got here? Fourier transform of Rx of tau is equals to what? 2 by 1 plus j omega. So 1 plus omega square. So now we got Sx of omega, nothing but the power spectral density of input. Now we have to calculate what? The transfer function of the system, which is obtained by taking the Fourier transform of the impulse response. So what is impulse response? In the given problem they are given as e power minus 2t for t greater than or equals to 0. So what is h of omega then? Fourier transform of h of t. So what is the Fourier transform of h of t? Integration minus infinity h of t into e power minus 2t dt. So that equals to, so in the given problem only for positive values it is e power minus 2t. So when t is less than 0 is 0, therefore we can replace the limit as integration 0 to infinity, nothing but for positive values of t. What is the function here? They are given e power minus 2t into e power minus j omega t. So e power minus j omega t dt. That equals to integration 0 to infinity. If you take e power minus t common, then you are going to get 2 plus j omega into dt. So if you take the integration, then you are going to obtain e power minus t into 2 plus j omega by minus of 2 plus j omega, and the limits are from 0 to infinity. So that equals to, then what can you obtain if you substitute the upper limit? E power minus infinity is 0. So if you substitute the lower limit, you will get, so minus of e power is nothing but what? 1. So you will get 1 by 2 plus j omega. Therefore, what is h of j omega? You got 1 by 2 plus j omega. And what is Sx of omega? You got 2 by n plus omega square. Therefore, what is the power spectral density of the output? The PSD of the output y of t nothing but Syy of omega equals to Sx of omega into mod of h of omega square. So what is Sx of omega? 2 by 1 plus omega square into mod of. So what is h of omega? You got 1 by 2 plus j omega. So here mod of 1 by 2 plus j omega whole square. So that equals to what? If you simplify, you'll get 2 by 1 plus omega square into, so 1 square nothing but 1 only. And what is mod of 2 plus j omega? Square root of 4 plus omega square. So here what can you obtain here? And here square root and square root get cancelled, get here 4 plus omega square. So like that you can calculate if they give the impulse response to the system and the autocorrelation of the input of the entire system, then you can calculate the power spectral density of the output by using this relation, that nothing but Syy of omega equals to Sx of omega into mod of h of omega square. And the second problem here is a wide sense stationary random process x of t is applied to the input of an entire system whose impulse response is 5t e power minus 2t for t greater than 0. And they have given the mean of the random process x of t is 3. Find the mean of the output system. Nothing but they have given the mean of the input, nothing but the random process, nothing but here they have given as 3. So let us say this is a LDA system whose impulse response is h of t and this input is x of t, the random process. The output is nothing but y of t, which is given by what? X of t convolution h of t. And they are given the average value, the mean of the input x of t equals to what? 3. So it is constant, nothing but whatever the value of t, that value equals to what? 3 only. And they are given the impulse response h of t equals to 5t into e power minus 2t. For what values of t? When t is greater than equals to 0, they have given. So now what you have to calculate? You have to calculate the mean of the output system. So what is y of t here? It's nothing but the convolution of the given input, random process input x of t, and then the impulse response h of t. Now what is expectation of y of t? Nothing but the mean of y of t. That is nothing but what? The mean of the output of the system y of t is equals to what? Expectation of, what is y of t here? X of t convolution h of t. That equals to expectation of, what is the convolution formula? Nothing but what? Integration. So this is nothing but expectation of h of t convolution x of t also, because The convolutional property satisfy the commutative law. Therefore, what is a convolution of h of t and x of t? Nothing but what? Integration minus infinity h of lambda into x of t minus lambda d lambda. And then you can write down this what? So expect integration minus infinity h of lambda into, because here the expectation will be calculated only with respect to what? The random process. In this, which is a random process, the impulse response is constant. So which is a random process here? X of t minus lambda. Therefore, you can write down this as what? Expectation of x of t minus lambda into d lambda. Now what they have given? The mean of the random process, the input random process x of t equals to 3. So whatever the value of t, it is constant. T may be t1, it may be t2, or it may be t minus lambda. Its mean is constant. The value is equals to what? 3. Therefore, 3 into d lambda. So that equals to 3 into integration minus infinity h of lambda into d lambda. So that equals to 3 into what is h of lambda I got? From 0 to infinity it is, from 0 to infinity nothing but 5t into e power minus 2t. So 5t e power minus 2t for t greater than equals 0. So here in place of t, I have the variable lambda. Therefore, I can write down h of lambda equals to 5 lambda into e power minus 2 lambda for lambda is greater than equals 0. Therefore, here 5 lambda into e power minus 2 lambda. So 5 lambda into e power minus 2 lambda into d lambda. So 3 into 5 nothing but 15 integration 0 to infinity lambda into e power minus 2 lambda d lambda. So we have to apply the integration of mu formula. Then you can write this as what? So 15 into, so what is integration of u into v? Nothing but u into integration of u. What is integration of e power minus 2 lambda by minus 2 minus integration of, so what is lambda? What is the differentiation of lambda? Nothing but 1 into, so what is integration of e power minus 2 lambda by minus 2? Nothing but e power minus 2 lambda by 4. So directly can write down here, no need of writing again. So, and what are the limits of lambda here? 0 to infinity. Then you can obtain 15 into, substitute the infinity here, the upper limit. So, infinity into e power minus infinity. What is e power minus infinity value? 0. So, 0 into infinity, what you can obtain here? 0. Minus, here also e power minus infinity is 0. So, therefore the upper limit is 0. So, minus of, what is the lower limit here? 0. So 0 into e power 0. 0 into something you will get 0 here. So minus of minus will get plus. So plus 1 by 4. That equals to what? 15 by 4. So therefore this is what? The mean of the output random process y of t, which is nothing but 15 by 4. So next question they have given is, a random process x of t has an auto-correlation function Rx of, this is tau. So Rx of tau is equals to a square plus b into e power minus mod tau, where a and b are positive constants. So find the mean value of the response of the system having an impulse response h of t equals to e power minus kt for t greater than 0 and 0 for t less than 0, where k is a real positive constant for which the x of t is input. So it means they are given x of t. For this system, h of t is the impulse response, the input is x of t, and its output is nothing but here y of t. So what you have to calculate? You have to calculate the mean value of the response of the system. So what they have given first? So they have given x of t is the input function, because they are given that x of t is its input, and what is the auto-correlation function? Rx of tau equals to a square plus b into e power minus mod tau. After that, what they are given? They are given the impulse response h of t equals to e power minus kt for what values of t? When t greater than 0, and 0 for t less than 0. So they have given the impulse response, they have given the auto-correlation function. What you have to calculate? You have to calculate the mean of the output random process y of t. How to calculate? In the previous problem, instead of giving the auto-correlation function, they have given the mean of the input. Now they have given that the autocorrelation function. If you observe this autocorrelation function is a function of only tau. Therefore, you can say that the given random process x of t is a wide and stationary random process. So now Rx of tau they have given as what? A square plus b into e power minus mod tau. Now from this autocorrelation function, how do you calculate the mean of the random process? So for that you have to use the properties of autocorrelation function. So from the properties of the autocorrelation function, so then limit mod tau tends to infinity, Rxs of tau is equals to what? E of x of t whole square. So this is can write down from the properties of autocorrelation function, which already we have discussed in the previous lecture. Therefore, so limit mod tau tends to infinity. What is Rx of tau in given problem? A square plus b into e power minus of mod tau is equals to, so the mean of the random process. What is E of x of t? Nothing but the mean of the random process input. So therefore, if you substitute tau equals infinity, then what can happen here? A square plus b into e power minus of infinity equals to E of x of t whole square. So what is e power minus infinity value? 0. Therefore, a square is equals to what? E of x of t whole square. From this, what is E of x of t? The mean of the input random process x of t equals to a. Now we got the mean of the random process input. Now, what is the mean of the output random process? E of y of t is nothing but what? So E of x of t convolution h of t. Since convolution satisfying the commutative property, you can write this as what? Expectation of h of t into x of t also. What is the convolution formula? Previously I have seen here. So expectation of integration minus infinity h of lambda into x of t minus lambda d lambda. That equals to, what is the expectation? Always find it with respect to the random process. Therefore, this is constant here. Therefore, this is integration minus infinity h of lambda into expectation of x of t minus lambda into d lambda. So, you got E of x of t equals to a. It means it is not depending upon t. So, for all values of t, it is constant a only. T may be anything. So, for t equals to t minus lambda also, it is a only. Therefore, this value is equals to integration minus infinity h of lambda into a into d lambda. So, that equals to integration. What is h of lambda they are given? E power minus kt. So, 0 to infinity, what is that? Well, for positive values, e power minus kt, and a is constant, bring it outside into dt. That equals to what? A into integration of e power minus kt with respect to t is e power minus kt by minus k, and the limits are from 0 to infinity. So, if you substitute what can happen here? A by k, nothing but a into 1 by k, that is nothing but a by k. Like that, you can calculate the mean of the output random process y of t. Next, what they are given here, a random process x of t is applied to a network with impulse response h of t equals to u of t into e power minus bt, where b greater than 0, which is a constant value. So, the cross correlation function of x of t with output y of t is known to have the form rxy of tau. So, this is rxy of tau is equals to what? Tau into e power minus b tau into u of tau. So, find the autocorrelation function of y of t, and then what is the average power in y of t. So, what they have given here? They have given x of t is the input, and they have given the impulse response to the system is t into e power minus bt into u of t. And they are given the cross correlation function of the input with output. Nothing but they are given rxy of tau is equals to what? Tau into e power minus b tau into u of tau. Now, what you have to calculate? You have to calculate the autocorrelation function of the output. Nothing but you have to calculate ryy of tau. This is the first problem. And second problem is what? What is average power in y of t? Nothing but what is P average. So now, how do you calculate the autocorrelation function of phi of t? So before that, what is the relation between the cross PSD and the PSD of the input? Nothing but the cross PSD of the input and output is given by what? Sxy of omega equals to Sx of omega into h of omega. So what is Sxy of omega? So the Fourier transform of the autocorrelation, the cross correlation function only. Therefore, so if you calculate Sxy of omega, if you calculate h of omega, you can calculate the autocorrelation, the power spectral density of the input. From that, you can calculate the power spectral density of the output. From that, you can calculate the autocorrelation function of the output. Therefore, what is the Rxy of tau they have given? They have given nothing but what? Fourier transform of, so t into e power minus bt into u of t. So what is the formula here? Integration minus infinity. So t into Fourier transform formula I down here into e power minus j omega t dt. In place of x of t, you have t into e power minus bt into u of t. And what is u of t? Only for positive values that equals to 1. So what is u of t? The unit step function that equals to 1, 1 for t greater than equals 0 and 0 for t less than 0. Therefore, replace limits from 0 to infinity t into e power minus bt into e power minus j omega t dt. That equals to what? Integration 0 to infinity t into e power. If take minus t common, you will get b plus j omega into dt. Now you have to calculate integration of t into nothing but you have to use the uv formula. Then what can obtain here? So what you can here 0 to infinity. So what is this? Nothing but Sxy of omega is equals to what? T into e power minus t into b plus j omega into dt. This is u, this is v. Then how could I write down this as integration of uv, nothing but u into integration of v, nothing but. So integration of uv equals to u into integration of v minus u dash into integration of v. So use this formula to calculate here. So t into the integration of v is e power minus t into b plus j omega by minus of b plus j omega minus, and the integrate, what is the differentiation of t? Nothing but 1. And again the integration of this function is what? E power minus t into b plus j omega by, so minus into minus get plus, so b plus j omega square. And what are the limits of t here? From 0 to infinity. Then if you substitute the upper limit, you are going to get 0 here. So if you substitute the lower limit, then what can happen here? 1 by b plus j omega whole square. This is nothing but what? Sxy of omega. And what is h of, this is nothing but h of t. So what is Rxy of tau? E power tau into e power minus tau, e power minus b tau u of tau. What is this values are in place of t here? U of tau. So e power tau into e power minus b tau u of tau. So in place of variable t, just replace by tau, because they have given the cross correlation function in terms of tau. Therefore, replace t by tau here. Then you can obtain, so replace t by tau here. So therefore, minus of tau, and here, so what is Xy of omega? Got 1 plus j omega square. Similarly, what is h of omega? Fourier transform of h of t. What is h of t here? T into e power minus bt into u of t. It is same only, but in place of tau we have here t. Therefore, what is the answer going to get? 1 by b plus j omega whole square. Then what is Sxy of omega equals to cross PSD is equals to the PSD of the input into the transfer function h of omega. So from that, what is Sx of omega equals to Sxy of omega by h of omega. What is the cross PSD of the input and output? 1 by b plus j omega square. And what is h of omega? 1 by b plus j omega square. Therefore, what is Sx of omega you got? Is equals to what? 1. And here what is Sxy of omega you got? 1 by b plus j omega square. And what is h of omega? The transfer function you got? 1 by b plus j omega whole square. Then what you have to calculate? Then what is the PSG of the output relation? SYY of omega equals to what? Sx of omega into mod of h of omega square. So therefore, you can obtain from this, what is x of omega? 1 into mod of h of j omega. So what is h of omega here? 1 by b plus j omega square. So 1 by b plus j omega square. Now if you want the autocorrelation function, what can I have to do? Is equals to, then what can I obtain? Inverse Fourier transform of what? 1 by b plus j omega square. Then you will get the autocorrelation function of the output. This is the first problem. And what is the second problem? You have to calculate the average power. How can you obtain the average power? That is nothing but what? So mod of h of omega whole square here. It means inverse Fourier transform of 1 by b plus j omega whole power 4 here. So mod here, that is nothing but what? 1 by b square plus omega square whole power 4. So 1 plus 1 by, so what is mod of 1 by b plus j omega? So 1 by b square plus omega square whole square. Therefore here again 1 by b square plus omega square whole square. So here what can I obtain? Inverse Fourier transform of 1 by b square plus omega square whole square. So that you are right on. So that you are going to obtain the autocorrelation function. And what is the P average equals to? So 1 by 2 pi integration minus pi to pi SYY of omega d omega. RS you can write down RYY of 0 also. So like that you can calculate the average power by substituting SYY of omega is nothing but the PSG of the output. RS in this autocorrelation function substitute of equals 0, then you are going to obtain the average power. So like that you can solve the problems on the power spectral density of the input and output of a system. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.